Now that you have some experience with electric fields and forces, we'd like to introduce a concept called electric flux. You probably already have some kind of intuition for what this is, as you'll see in a moment. Electric flux is represented by the number of electric field lines that will penetrate some surface. Say if I'm given some surface like this square surface here with some area A, and there's an electric field penetrating through it, I could intuitively think of the flux as being the number of field lines that actually penetrate through the area. So if I could count how many field lines were actually going through that area, that would give me a number for electric flux. In a sense, I'm trying to find what the flow of the field is through a given area. This would be independent of the shape of the surface itself. Say if I had a curved area like this hemisphere over here, but if I had the same field going through that surface, I would have the same flux. In other words, the flux is indeed how many of these field lines are actually going through a given surface area. And in this case, it wouldn't matter whether it was a square plane or a curved area. If I have the same number of field lines going through, I have the same flux. So if I had a planar surface like above, I can characterize the flux in terms of mathematically as being equal to, and I designate flux by this phi symbol here. Kind of looks like a fighter in Star Wars. The phi symbol flux is equal to the magnitude of the field, E, times the magnitude of the area, A. In a sense, I can see that this should give me some quantity of how many field lines are actually going through the area. Because if I were to increase the field, I would have to indicate that by drawing more arrows. And hence I'd have more flux lines indicating a stronger field proportionally. Hence, I'd have more lines. So the larger E is, the more lines I would have, and hence I'd have more flux lines. Same thing with A. We're presuming that we have this field all the way through some expanse, and if I were to increase my area, I would encompass more of these field lines, hence I'd have more flux lines, and hence the flux would increase in that way as well. So if I increase either the field or the area, I'm going to get more of this flow of the field, more flux lines going through that area. In general, if I had a planar surface, the flux is equal to the dot product between the E field and the area vector for that surface. This allows me to move the orientation of the area so that I can account for that. I mean, if I were to move the area at an angle, I might encompass less flux lines. I need some way to think about that. This area vector is a vector that is normal to the surface of the area it represents, and the magnitude of which is equal to the area that it represents. Here's how it might look. Let's say I had a flux moving like this through some planar area, this rectangle here, and then I had another rectangle at an angle here with larger area, but in both cases I have the same flux going through both of those areas. I have these flux lines going through the first one and the same flux lines going through the second one. So they both have the same flux. Now if I looked at this second area, I could represent it by an area vector, a vector that has the magnitude equal to that area, and then a direction that's normal to the plane of that area. And I can describe the flux then through this larger area as being equal to the magnitude of the field times the magnitude of that area times the cosine of the angle between the field direction and the area vector. I could see that this should be the same as the flux that's going through this perpendicular area down here, because if I were to look at this triangle down here, it'd be a right triangle with angle theta, and the area of the hypotenuse would correspond to the area of this side here by a cosine theta. So in either case, if I use E a cosine theta where there's an angle between them, or E times a cosine theta where there's no angle between them, they're in the same direction, I get the same flux. So all the while, you want to keep in mind in this discussion that flux is how many field lines are going through an area. If this surface were not flat, let's say it was a curved surface, I can imagine a expansion of this treatment that we've been talking about by thinking of a curved surface as being a lot of little infinitesimal flat planes all the way around the curved surface, and I have my dot product of the E field with every one of those little planes. And if I were to superimpose and add all those contributions together, I would get the flux that's going through that curved surface. In the infinitesimally small dAs, and that summation, that basically gives me an integral of E dot dA for all those planar surfaces along a continuous surface. So now I can represent my flux as this. Flux is equal to the integration over some surface area of the E field dotted with the area vector everywhere on that surface area. We say the net flux is the number of lines that leave the surface minus the number that enter a surface. So flux that is leaving a surface is going to be a positive flux. It's going to be directly in line with the area vector on that surface. Flux that's going into a surface is going to be negative because the area vector normal to the surface outward is always going to be in the opposite direction. So flux that's going in is negative. Flux that's going out is positive. The difference between the two, what's going out versus what's going in, is going to be your net flux through a surface. Let's try this out with an example. Let's find the flux through a cube. Consider a uniform electric field, E, oriented in the x direction. Find the net electric flux through the surfaces of a cube of edge length L, oriented as shown in this figure. So in this case, we have an electric field moving in the positive x direction, and it's going to encounter a cube. Let's just use this box here. It's going to encounter this cube going in the positive x direction, and the flux is going to enter this side, come out this side, and we have area vector everywhere normal outward from this cube. So let's consider the top face of this cube first. How much flux is going through the top face of this cube? I got this flux coming in like this, and I'm wondering how much flux is actually going through this top face. Well, if these are parallel lines going in like this, they're going to continue to be parallel lines. They're not going to bend and go through this top face. So my intuition tells me there should be no flux through the top face of this cube, and I should be right. If we calculate that, we would say that the area vector at the top face is pointing up like this. The E field is going in the positive x direction. There's an angle of 90 degrees between those two vectors, and the cosine of 90 is 0. So there is no flux going through that top face. That's what we would conclude mathematically, just like our intuition told us. By symmetry, this would also be true for the bottom face as well. If these flux lines are coming in like this, they're not bending to go through the bottom face. They're continuing through parallel, and hence there's no flux going through the bottom face as well. Mathematically, the E field's going this way, the area vector of the bottom face is going down, and there's a 90-degree angle there. Cosine 90 is 0. No flux through the bottom face of this cube. What about the front face? These lines are going like this, and they're not bending to come out through the front towards you, and hence there's a 90-degree angle again because the area vector is coming out towards you. The E field is going this way, 90 degrees between them, cosine 90 is 0. No flux through the front face of this cube, and for that matter, there's no flux through the back face of this cube for the same reasons. So there are four faces of this cube, top, bottom, forward, backward, where they have no flux because E dot dA is equal to 0, and intuitively the flux lines are not going through those faces. Okay, so the only two faces we need to consider for this cube as far as flux is concerned is the left face and the right face as you're looking at it. If I consider the right face, the field lines are coming parallel out like this, and in the same direction the area vector is pointing out normal to the surface like this. They're both in the same direction, so there's an angle of 0 degrees between them. Cosine of 0 is 1, so E dot dA is equal to E dA. E is constant on that surface. Take it out of the integral, and then we would integrate simply over the area of that right face. Well, the edge length is L, so the area of that right face is L squared. So our flux through the right face of this cube is EL squared. What about the left face? Flux lines are coming in this way. The area vector is going normal to the surface outward in the negative x direction, if you will. And there's going to be 180 degrees opposite direction to the two vectors. So we're going to have EDA cosine 180, which will cosine of 180 will give us a -1. Integrate that over the left face, and we get a flux of a negative EL squared for that. So the flux that's going in is a negative flux. The flux that's coming out is a positive flux. The net flux, the flux going in on the left plus the flux coming out on the right, would be a negative EL squared plus EL squared, which will give us 0. So there is no net flux through this cube. And there is flux, but it's net flux. Whatever is going in is coming out in the same magnitude. So these are our observations for the cube. There's no E field lines through the other four faces, top, bottom, front, back, because there's no flux lines going through those faces. Concerning the last two faces, what goes in comes out. So we've got this flux going in, but it's also coming out. So there is no net flux through this cube if the E field originates from outside the cube. So here's a cube. We have some external E field. If the E field originates from outside, there will be no net flux through the cube. What goes in comes out. What would happen, though, if I were to rotate this field? So instead of going in the positive x direction, I were going at an angle like this. Flux is coming up like this, coming out over here like this. Well, it'd be a little bit harder calculation. I'd do E dot dA for these flat surfaces here, and I'd get some kind of negative flux coming in. And then I'd do E dot dA for these flat surfaces over here, and I'd get some kind of positive flux coming out. But when all was said and done, and I did the mathematics, I'd still come up with no net flux through this cube. And it wouldn't matter what direction this external field was going into the cube. Eventually, I'd realize that there was no net flux through this cube. I know this intuitively because whatever lines are going in are coming out. So all external flux goes in and comes out of the cube. As long as the E field doesn't begin from inside the cube, the net flux to this cube is 0. If the E field begins from outside the cube, I'm going to have a flux, net flux of 0 through the cube. This was true for a cube, but this would be true for any closed surface that had an external electric field. If I have a closed surface and the electric field is outside that surface, the flux lines would go in and then come out, giving me a net flux of 0 in every case, no matter what the orientation. Here's another example. I have a closed surface. It's near a point charge, a positive point charge, and we know point charges produce electric flux lines, and they go in all directions, radially outward, in all three-dimensional directions. So in the vicinity of this closed surface, I'm going to have flux lines going in, but then they're also coming out on the other side. So whatever number of lines are going in on this side, are coming out on this side, and even though the lines are not parallel, in this case, they're still going in, coming out. So the net flux in this case is still 0. So up to this point in this lecture, pretty much what I've taught you is 0, nada, nothing, because the net flux is 0. But we still have learned something, hopefully. We've learned enough to try a problem. A pyramid with a 6-meter square base and a height of 4 meters is placed in a vertical electric field of 52 newtons per coulomb. Calculate the total electric flux through the pyramid's 4 slanted surfaces. So I have a pyramid. It's got 4 triangular slanted surfaces and then a square base. And I want to find what is the electric flux through those triangular slanted surfaces. That could be a hard problem. I mean, I'd have to figure out the area of those surfaces. I'd have to figure out the angle, do the dot product, figure it out, and it's not impossible. It's not that hard, but it would take some time to do that. What we're going to use, though, is the fact that the net flux to this pyramid should be 0. So whatever's coming in through the base is coming out through the 4 slanted sides. And hence the magnitude of the flux that's going in through the base is equal to the magnitude of the flux that's coming out through the 4 top sides. The positive flux exiting should be equal in magnitude to the negative flux as entering the base, because the total flux would be 0. The flux going into that flat base is just the E field times the area of the base, cosine of 180 degrees because the area vector is pointing down, normal to the outside surface, as the flux, the E field, is going up. So we have a negative area that, or the field is 52 newtons per coulomb, area of that base is 6 meters squared, and then cosine of 180 is negative 1. So we have a negative 1.87 times 10 to the 3 Newton meter squared per coulomb. There is no set unit for electric flux in the SI system. It is Newton meter squared per coulomb. We're waiting for somebody to do something great in the field of electric flux so that we can put their name on the electric flux unit. So if you do something great concerning electric flux, we can put your name on the electric flux unit instead of dealing with Newton meter squared per coulomb. Something to strive for. So this is our total flux that's going into the base. What's coming out on the other side should be the positive magnitude of this, and hence the flux through one of the 4 slanted sides. By symmetry, there shouldn't be any more going through one slanted side as opposed to the other. So the flux through one slanted side will be 1/4 of this total flux. So the flux through one slanted side is 1/4 of 1.87 times 10 to the 3, which is 4.68 times 10 to the 2 Newton meter squared per coulomb. And that's the flux through one slanted side of the pyramid. Nice. All right, so we said that if we have a closed surface and the flux originates from outside that surface, the net flux is 0. But what would happen if you had a flux-producing device, like a charge, and you enclose it by the surface? Well, then you're going to have field lines going outward from this positive charge, say, in this sense, and you will end up with some kind of net flux through that surface. It's not going to be 0 because the lines are only going outward. This outward flux is proportional to the electric field, which in turn is proportional to the charge, because we know the charge is equal to kq over r squared. So the field is proportional to the value of the charge inside. So we could say that the flux that goes through this curve is proportional to the charge inside. And for our proportionality constant, Let's just choose 1 over epsilon naught. Why not? So we're just going to select some kind of constant. It'll become important in a moment. But we're just saying that the flux that goes through this closed surface is proportional to the charge inside. If the charge were increased, I would have to indicate that by drawing more flux lines for a greater field, and hence my flux would be increased proportionally. The same amount of flux lines will leave this surface of this sphere regardless if I were to change the surface type. If I change it from a nice sphere that I have right now, to some weird glob, weird conglomerate surface like this, I still haven't changed the number of flux lines that are leaving this surface. So the flux is still the same regardless of the way my surface looks, how big it is, how small it is. It doesn't change. I still have the same flux lines going outward. So the flux is still proportional to the charge enclosed. The flux will equal the charge enclosed divided by epsilon naught. This is kind of neat because if you were trying to calculate the flux, for calculation purposes, you can choose the easiest surface to enclose the charge. You don't have to use the surface that you were given, because if you're just trying to find the flux, it doesn't matter what surface you were given. You could have any surface. So you're going to choose a surface that will make your calculation the easiest calculation possible. So that's kind of cool. You have that choice. The choice of the surface you'll make is what we're going to call a Gaussian surface, for reasons we'll explain later. But you would choose a surface regardless of the surface that you were given, so that you can make the calculation easier. There's a reason why we're doing all this, why we're discussing flux. We're headed towards something, and I'm going to give you that reason. You may have heard earlier that I was working on time travel, and I've hit a few snags in my analysis. Here's a picture of one of my experimental apparatus. It's a DeLorean, and you might recognize the flux capacitor in the center of this experimental apparatus. I've crashed a few of these. I've lost a few, I've misplaced a few volunteer students. I'm going to get them back someday if I can figure out where we put them in history. So in order to continue this research, I just need a few more volunteers. So if you want to make some extra credit, just let me know. I'll accept volunteers to try out my latest adaptation of the time machine. Take a look at this. A spherical Gaussian surface surrounds a point charge Q. Describe what happens to the total flux through this surface if the charge is tripled. So I have this charge enclosed in this surface. What's going to happen if I triple the charge, increase it by 3 times? Well, if I were drawing the electric field lines, if I increase the charge by 3 times, I would have to draw 3 times as many lines to indicate the stronger field. Hence, the flux that would go out through the surface would be 3 times as much. So the flux is proportional to the charge, and if I triple the charge, I'll have 3 times the flux. What would happen if I doubled the volume of this sphere that's enclosed in this charge? So I have one sphere that's enclosing a charge. If I increase the volume to twice as much, what will happen to the flux? Well, it'll still be the same flux. The same lines that were going through the first sphere are going to continue onward through the second sphere. So it doesn't matter whether my sphere got bigger or smaller. I'm still going to have the same number of lines, and we're still going to have the same flux through either surface. What would happen if I changed the sphere into a cube? What would happen to the total flux through that surface? Still would be the same. Whether I have a sphere, I'm going to have those flux lines going out. If I change it to a cube, same flux lines. So it doesn't matter whether I have a cube or a sphere, I'm going to have the same amount of flux going through that surface. It's still going to be proportional to the charge inside. So I probably want to choose a sphere because that's going to have more symmetry than, say, a cube. What happens if I move the charge to another location inside the surface so it's not centrally located? I'm going to move it to one side. What's going to happen to the total flux through that sphere? Well, it's going to be more dense on the side that I moved it to because the lines are going to be closer together and more dense there, and more spread out on the other side. But I'm still going to have the same number of lines eventually exiting that sphere. So even though I moved it off center, I'm still going to have the same total flux going through that sphere. It's just going to be a little bit more dense on one side as opposed to the other. So still no change. Let's try an example. A point charge, big Q, equal to 5 microcoulombs, is located at the center of a cube of side length 0.1 meters. In addition, 6 other point charges, having little q equal to negative 1 microcoulombs, are symmetrically located around big Q. Determine the electric flux through one face of this cube. Well, everything's symmetric, so there's no reason why one face would have more flux than any other face. So if I could find the total flux going out of this cube, I could divide that by the 6 faces of the cube and find the flux through one face by symmetry. So that's what I'm going to do. And I know that the total flux going out of this cube is proportional to the charge inside. So let's calculate that. The net flux to this cube is equal to 1 over epsilon naught times the total charge inside, big Q plus 6 times little q. That's going to be 5 times 10 to the minus 6 for 5 microcoulombs, plus 6 times a negative 1 times 10 to the minus 6 for negative 6 microcoulombs over epsilon naught, which is 8.85 times 10 to the minus 12. That gives me a negative 1.13 times 10 to the 5 Newton meter squared per coulomb. What does the negative sign mean? Well, if I'm considering net flux, in this particular case, I actually have more lines that are coming into this cube than are going out. So my net flux is actually negative. I'm enclosing more negative charge than positive charge, so those flux lines are always coming into the negative charge. I have more negative flux into this cube. By symmetry, there's no reason why one side of this cube would have more flux than another side. Everything should be distributed equally. So I'm going to divide my total flux by 1/6 for the 6 sides of the cube, and that'll give me a negative 1.88 times 10 to the 4 Newton meter squared per coulomb. That's the flux going through one side of this cube. Not too difficult to calculate to do this. All right, so we've been talking about flux, and there's really 3 ideas we've thrown out there about flux. One of them is just your pure intuition. The intuition of flux is if you have field lines, how many of those lines are going through an area? And so the more lines you have, the more flux and that sort of thing. You should always be thinking about this in order to better your understanding of a particular situation. Always be thinking about the field lines going through an area. That's your flux. But our other 2 things were mathematical. We had 2 flux representations. We said that if we had a curve, that the flux is equal to the E field dotted with the area vector everywhere on that curve, on that surface. And we said that if a closed surface encloses a charge, the flux is proportional to the charge inside. So, what would happen if you had a closed surface and you calculate the flux through either method? They should be the same. So we should say that the integral of the E field over the area of a closed surface should equal the flux due to a closed surface, the charge inside divided by epsilon naught. So we're simply saying flux equals flux. This is Gauss's law. and is one of the most famous laws in science. It is one of the four major Maxwell equations that describe all electromagnetic phenomena, and basically the Maxwell equations is regarded as one of the greatest theoretical achievements of all time. Gauss's law is one of those equations. It's a relatively simple equation, but we can use it to calculate electric fields, and it's based on this idea of flux. Flux equals flux. So you are looking at Gauss's law. Any surface can be chosen to enclose this charge. You can choose any surface. We saw it didn't matter what surface you use to enclose the charge. So we're going to find a surface that makes the calculation, especially of this integral, easier. In other words, we're going to choose a surface that has symmetry that will allow us to calculate E dot dA over that surface so that we can use this law in the simplest way possible. So we'll choose a Gaussian surface that will have spherical symmetry if the lines are radially outward or have spherical symmetry themselves. We'll choose a Gaussian surface that has cylindrical symmetry. For instance, if we had a line of charge, like this ruler, then we might choose a Gaussian surface that is a cylinder around this ruler, because the E field would be going radially outward through the surface of that cylinder, and it would be constant on that surface. So we choose a cylinder in that case. Or planar symmetry. If we had a plane parallel E field, then we might choose a Gaussian surface that's just a plane, or some kind of surface that has planar sides. And we'll use that to calculate the E field in that particular case. So a quick review of Gauss's law. We have that if we had a surface, every bit of flux that goes through that surface is a projection of the E field with a normal area vector everywhere on that surface, the dot product. Add up all those contributions, which is our integration, and the flux is equal to the integration of the E field dot with the area vector everywhere over that surface. We also had that if we had a charge inside the surface, the flux through that surface is proportional to the charge inside. It's equal to the charge inside divided by epsilon naught. Combining these two, flux equals flux, we get Gauss's law. Well, what can we use Gauss's law for? We generally use Gauss's law to calculate electric fields, and the simplest, or probably the most basic example of the use of Gauss's law is this. Derive Coulomb's law starting from Gauss's law. And this is going to be very important. We're going to derive Coulomb's law from Gauss's law. We're going to start with a point charge. Positive point charge emanating electric field radially outward in all directions. We're going to enclose this charge by a Gaussian surface. We'll call it a Gaussian surface. We can name it after you, but since we're using Gauss's law, we'll just call it a Gaussian surface. A surface of our choice, but we're going to choose a Gaussian surface that has a symmetry to the charge distribution that we have. In this case, if we have a point charge, we'll choose a sphere around that point charge. And then we're going to apply Gauss's law to this surface. So E dot dA is equal to charge enclosed over epsilon naught. All right, we chose the right surface. We got a sphere, and we'll note that if this charge is at the center of that sphere, the E field is going to be going radially outward everywhere on this sphere, and hence it will be parallel to the area vector everywhere over the surface of this sphere. There will be no place where they are not parallel. Hence, over this surface, E dot dA will be equal to E dA cosine 0, and cosine 0 is just 1. So E dot dA will become E dA at everywhere on this surface, and we have the integral of E times dA equals charge enclosed over epsilon naught. Also, Since we chose the charge to be at the center of the sphere, there's no reason why the E field would be more intense at any particular point on the sphere as opposed to any other point. In other words, the E field is going to be the same in magnitude all the way through this sphere because we're symmetrically located at a distance away from the same charge. So the E field will be constant on the surface of this sphere. That's important because that means I now have a constant inside the integral, which is the E field. And if I have a constant in the integral, I can take it out of the integral. So that's what we're going to do. We're going to pull our constant out, and now we have that the E field times the integration of this area over the surface is equal to the charge enclosed over epsilon naught. But the integral of a surface area over a sphere is just the area of a sphere, and that is 4 pi r squared. So our integral dA is 4 pi r squared, and now our equation looks like this. E times 4 pi r squared is Q enclosed over epsilon naught. Solving for the E field, I get the E field is equal to Q enclosed over 4 pi epsilon naught times r squared, which is K, Q enclosed over r squared, where K is our famous K constant, 9 times 10 to the 9, but K is equal to 1 over 4 pi epsilon naught. This is the E field for a point charge, where our famous K constant is 1 over 4 pi epsilon naught. Pretty good. Now if I bring in a second charge and put it on the surface of this sphere, it's going to feel a force on it. It's going to feel a force equal to its charge times the field that exists there. So that force is going to be equal to Q naught E, which is Q naught times the field, which is K Q enclosed over r squared, because that's the field that exists at that radius from the first charge. So this is going to be equal to K times Q naught, Q enclosed, over r squared. By golly, that is Coulomb's law. So we have derived Coulomb's law from Gauss's law. How about that? I want you to memorize this derivation. Why? I haven't asked you to memorize derivations probably ever. But this one's really important because it is the basis for using Gauss's law. If you start from this derivation, a lot of the same ideas we used in this derivation we can use for all our applications of Gauss's law. So it's very important. And if you ever take a test in the electrodynamics course after this one, it's almost guaranteed that on your first test in that course, there's a good chance that this derivation will be on it. In other words, let's just say there's about a 50% chance that you will see this derivation, derive Coulomb's law from Gauss's law, on your first test in an electrodynamics course. It might even be about a 50% chance it could be on your first test in this course. So go ahead and memorize this derivation because it's really going to help for all the derivations of Gauss's law, the uses of Gauss's law that are yet to come. I'm going to stop this first lecture there. Our second lecture in this chapter is going to be about all these other examples of Gauss's law that we can use it for some great examples.